In the previous video in this series, we reviewed important concepts and techniques that we need for correctly drawing E2 stereochemistry. In particular, we reviewed how to draw a Newman projection. In this video, we will apply those concepts and techniques to problems that involve E2 stereochemistry. Now remember, the product from an E2 is an alkene. So when will an alkene have interesting stereochemistry? For example, you know that a tetrahedral carbon has interesting stereochemistry when it's a stereocenter. When a tetrahedral carbon is a stereocenter, it has interesting stereochemistry. On the other hand, when a tetrahedral carbon is not a stereocenter, it has no interesting stereochemistry. Well, what about for an alkene? We know that alkene carbons are trigonal planar. When is the stereochemistry interesting for the trigonal planar carbons in an alkene? Well, we can't apply the idea of a stereocenter here. A alkene carbon would never be a stereocenter. An alkene carbon would never be a stereocenter because it's only attached to three things. But nevertheless, alkene carbons can have interesting stereochemistry. When do alkene carbons have interesting stereochemistry? An alkene has interesting stereochemistry if one of the alkene carbons is attached to two different groups, and the other alkene carbon is also attached to two different groups. For example, this alkene has interesting stereochemistry because carbon 1 is attached to two different groups, a methyl and an ethyl, and carbon 2 is also attached to two different groups, a methyl and an ethyl. How would we describe the interesting stereochemistry here? Well, we could say that this methyl group is cis to this methyl group, and we could say that this methyl group is trans to this ethyl group. That's how we could describe the stereochemistry. Would it make a difference if we swapped this methyl with this ethyl? Would that give us a different molecule? Well, yes, this is a different molecule. Notice that how would you describe the stereochemistry now? Now you would say that the methyl group is cis to an ethyl, and that the methyl is trans to the other methyl. Well, that's different from the pattern in this case. So I hope you can see that these are two different molecules. And remember, they really are different because there's no free rotation around a double bond. If you make this product, the methyl cannot easily rotate to this position. If you make this product, it's stuck in this configuration, and if you make this product, it's stuck in this configuration. So if you produce a product where the methyl groups are trans, they're stuck in the trans positions. And if you produce a product where the methyl groups are cis, they're stuck in the cis positions because there's no free rotation around a double bond. Notice that this molecule also has interesting stereochemistry. According to this rule, this alkene carbon is attached to two different groups, an ethyl and a methyl, and this alkene carbon is also attached to two different groups, a methyl and an ethyl. How about this example? Pause the video and determine whether you think that this alkene has interesting stereochemistry. Well, we could apply this rule. There's interesting stereochemistry if each alkene carbon is attached to two different groups. Well, notice here that carbon 1 is attached to two identical groups. Since carbon 1 here is attached to two identical groups, there is no interesting stereochemistry for this molecule using this rule. There's no interesting stereochemistry because carbon 1 is not attached to two different groups. Carbon 1 is attached to two identical groups, two methyl groups. And I hope you can see that there's no interesting stereochemistry here. Of course, you could say that this methyl group is cis to this methyl, but you could also say that this methyl group is trans to this methyl. One methyl is cis and one methyl is trans. Notice that what would happen if we swapped these two groups? If I move this group up here and I move this group down here, notice that it's still the same molecule. That's the sign that there's no interesting stereochemistry here. It doesn't matter which group you put up here and which group you put down here because they're both the same. If you swapped them, you would get the same molecule. Notice that if I swapped this group and this group, I would get a different molecule, this one. If I swapped this group and this group, I would get a different molecule, this one. That indicates that these two molecules, that the arrangement in space of these two molecules is interesting. These molecules have interesting arrangement in space because if you swap the arrangements in space, you get a different molecule. On the other hand, the arrangement in space of these groups is not interesting because if you swap the arrangement in space, you end up with the same molecule. And of course, if you swapped these two groups, you would still get the same molecule. If you swap these two groups, you would get this molecule, but I hope you agree that this molecule and this molecule are the same. In both pictures, we have one pair of methyls that are cis to each other and one pair of methyls that are trans. One pair of methyls that are cis and one pair that are trans. If you took this picture and flipped it 180 degrees around this horizontal axis, the picture would then look exactly like this picture. That shows that these two pictures are two different pictures of the same molecule. And that shows that flipping the position of this group and of this group doesn't change the identity of the molecule. So again, that indicates there's no interesting stereochemistry for this alkene. All right, so I hope that you would agree now that this rule does identify which alkenes have interesting stereochemistry and which alkenes do not have interesting stereochemistry. This is important because remember, E2 reactions make alkenes. If the E2 reaction is making an alkene with no interesting stereochemistry, then we don't need to worry about the stereochemistry of the product. But if the E2 reaction is making an alkene that does have interesting stereochemistry, then you do have to worry about the stereochemistry of the product. Now, here's an important fact about E2 mechanisms that we need to learn. In order for an E2 mechanism to occur, the leaving group and the beta hydrogen must be oriented in an anti-periplanar conformation. What that means is that the bond between the alpha carbon and the leaving group has to be pointing in the opposite direction to the bond between the beta carbon and the beta hydrogen. That opposite direction corresponds to anti. And periplanar means in the same plane. The bond between the leaving group and the alpha carbon has to be in the same plane as the bond between the beta carbon and the beta hydrogen. But we can really simplify this quite a bit. All you really need in order to get this anti-periplanar conformation is for the leaving group and the beta hydrogen to be located anti to each other in the Newman projection. If the leaving group and the beta hydrogen are located anti to each other in the Newman projection, you will have this anti-periplanar conformation. Now we can update our E2 guidelines. Here is a new guideline for E2 on a straight chain molecule. Now notice that the purpose of this guideline is to help us determine the stereochemistry of the E2 product. We do not always have to follow this guideline. You only have to follow this guideline if both the alpha carbon and the beta carbon are both stereocenters. If the alpha carbon and the beta carbon are both stereocenters, then a good method to determine the stereochemistry of the E2 product is, first, draw a Newman projection, looking down the bond between the alpha and the beta carbon. Then, rotate the Newman projection so that the leaving group and the beta hydrogen are located anti relative to each other. That reflects the anti-periplanar conformation between the leaving group and the beta hydrogen, which we know is required in order for an E2 mechanism to occur. When the leaving group and the beta hydrogen are anti in the Newman projection, they will have this required anti-periplanar conformation. So once you've accomplished that, now the substituents which are on the same side of the Newman projection will also be on the same side of the double bond. That tells you how to draw the correct stereochemistry for the E2 product. Obviously, we will be illustrating how to use this guideline on actual problems very shortly. Remember that you don't always have to use this guideline. We only have to use this guideline for a straight chain when the alpha and the beta carbons are both stereocenters. If the alpha carbon is not a stereocenter, or if the beta carbon is not a stereocenter, or if neither the alpha carbon nor the beta carbon is a stereocenter, then you don't need this Newman projection approach. Remember that a stereocenter is a carbon that's attached to 4 different groups. You may or may not see your professor and your textbook use a Newman projection in order to get the right stereochemistry for the E2 product. It's possible to figure out the correct stereochemistry without a Newman projection, but my experience is that beginning students make fewer mistakes if they use this Newman projection approach. Clearly, these ideas will make more sense when we start illustrating how to use them to solve problems. So let's start looking at some illustrations. Please pause the video and try this problem. Now let's discuss. I'll start by numbering all the carbons, including this carbon, and this carbon. We notice an ionic bond, so we draw in the formal charges for that ionic bond. We can identify that O- will be our nucleophile or base. Sodium plus will be the unreactive spectator ion. Neutral bromine will be our leaving group, and that means that carbon 3 is the alpha carbon because carbon 3 is attached to the leaving group. So we see that the alpha carbon is tertiary because carbon 3 is attached to 3 carbon chains: carbon 2, carbon 4, and carbon 7. Now use the table to determine the mechanism. Don't assume the mechanism is E2. A tertiary alpha carbon puts us in the bottom row of the table. O- puts us in the right-hand column of the table. So that tells us that the mechanism is indeed E2, and we should write down the name of that mechanism. Now we recognize that for an E2, we're going to use a base, not a nucleophile, and we know that O- is a strong base. We know that for E2, we want to label the beta carbons. Well, carbon 2 is a beta carbon, but carbon 4 is also a beta carbon, and carbon 7 is also a beta carbon because all 3 of those are attached to our alpha carbon. So we have to decide which of those beta carbons we're going to use in this reaction. Notice that the instructions said draw the major product. If the problem just told us to draw all the products, then we could use each of these beta carbons. But since they said to draw the major product, we should use the beta carbon, which gives us the major product. Let's follow these guidelines. We've labeled the alpha and beta carbons. Notice that all of these beta carbons have at least 1 hydrogen, so they're all candidates. So here's the rule for finding the major product for a straight chain. We're going to use the more substituted beta carbon. Well, notice that carbon 2 is a secondary beta carbon because it's attached to carbon 1 and carbon 3, 2 carbon chains. We have carbon 4 is a tertiary beta carbon because carbon 4 is attached to 3 carbon chains: carbon 3, carbon 5, and carbon 8. Carbon 4 is tertiary because it's attached to 3 carbon chains: 3, 8, and 5. And carbon 7 is a primary beta carbon attached to only 1 carbon chain: carbon 3. So we can see that the most substituted beta carbon is carbon 4. So for the major product, we're only going to use the more substituted beta carbon, carbon 4. So I'll erase this beta label, and I'll erase this beta label, because now we've seen that carbon 4 is the only beta carbon that we'll be using for this problem. Of course, we should check whether we're using tert-butyl oxide, because that would be an exception, but this is not tert-butyl oxide, so we don't use the exception. We use the usual rule of using the more substituted beta carbon. So now we've labeled the alpha and beta carbons that we're going to be using for this reaction. That's very important. Now we check whether the alpha and beta carbons are both stereocenters, and they are. The alpha carbon is attached to 4 different groups: an ethyl group, a methyl group, a bromine, and this complicated carbon chain. And carbon 4 is also attached to 4 different groups: a ethyl group, a methyl group, a hidden hydrogen, and a complicated carbon chain. Well, since both the alpha carbon and the beta carbon are stereocenters, this is where our approach is to draw a Newman projection to help us figure out the stereochemistry of the product. So let's draw that Newman projection. Notice that you should draw the Newman projection looking down the bond between the alpha and beta carbon. So here I've drawn a person's eye looking down the bond between the alpha and the beta carbons. Now you could draw the eye on the right side of the bond, or you could draw the eye on the left side of the bond, but it's probably best to be consistent. You'll probably make fewer mistakes if you're consistent. Well, in the previous example, I drew the eye on the right side of the bond. So to be consistent, I'm going to draw the eye on the right side of the bond here as well. Now we can start our Newman projection. Remember that the Newman projection has a dot and a circle. The dot represents the carbon that's closer to the eye. Carbon 4 is closer to the eye, so I'll label this dot as carbon 4. The circle represents the carbon that's further from the eye. Carbon 3 is the carbon that's further from this eye, so I'll label the large circle as carbon 3. From the perspective of this person, carbon 5 is pointing straight down. So I've labeled carbon 5 pointing straight down from carbon 4 and attached to carbon 6 in this picture. Then the other 2 bonds for carbon 4 would look like this. Here's the other 2 bonds for carbon 4. Where should I place carbon 8? Well, carbon 8 is on a dash behind the page. While this person's eye is in the plane of the page, the region behind the page is to this person's right. So carbon 8 would be pointing up from this person's perspective. Carbon 8 is pointing up from this person's perspective and to the right. We also have to show the hidden hydrogen, so let's draw that in. Since carbon 8 is on a dash, the hidden hydrogen should be on a wedge. Remember, a tetrahedral carbon has 2 solid lines, a wedge and a dash. And remember, draw the wedge and the dash adjacent to each other. Now, the hydrogen is on a wedge in front of the page. The space in front of the page is to this person's left. So the hydrogen should be pointing up and to the left in the Newman projection. Now we handle carbon 3. From this person's perspective, carbon 2 is pointing up from carbon 3, straight up. Here I've drawn carbon 2 pointing straight up and attached to carbon 1. Notice that carbon 2 should be attached to the circle, not to the dot, because carbon 2 is attached to carbon 3, not to carbon 4. I think it really helps to put in numbers in all of our pictures here in the Newman projection and the regular projection. Now let's see, the other 2 bonds for carbon 3 will look like this. Here's the other 2 bonds for carbon 3. The bromine is on a wedge in front of the page, and the space in front of the page is to this person's left. So the bromine ends up pointing down and to the left. From this person's perspective, the bromine is pointing down below the 3,4 bond and to the left of the 3,4 bond. And carbon 7 is on a dash behind the page. The space behind the page is to this person's right. So carbon 7 should be over here. From this person's perspective, carbon 7 is pointing below the 3,4 bond and to the right of the 3,4 bond. Behind the page is to this person's right, because this person's eye is in the plane of the page. Now that we've got the Newman projection, we have to rotate the projection so that the leaving group and the beta hydrogen are anti to each other. So can you find those in this picture? Here's the leaving group in this picture, and here's the beta hydrogen. Remember that maybe it would help to label these here. Carbon 4 is our beta carbon, and carbon 3 is our alpha carbon. So the beta hydrogen here is attached to the beta carbon, and the leaving group is attached to our alpha carbon. Well, in this picture, the bromine and the hydrogen are located gauche to each other. This is a picture where the bromine and the hydrogen are gauche from each other. And that's not what we want. We want them to be anti. Now, of course, the bromine is anti to carbon 8. The bromine and carbon 8 are anti, but that's not what we want. We don't want the bromine to be anti to carbon 8. We want the bromine to be anti to the beta hydrogen. So I'm going to circle these two groups because those are the groups that we're focusing on here. All right, so now we need to rotate this Newman projection to make these anti. We could do that by rotating carbon 4 one position clockwise. I'm going to rotate carbon 4 one position clockwise. Or maybe I should call it 2 positions. I'm going to rotate carbon 4 2 positions clockwise. I'm going to rotate this hydrogen to this position. Now, if I rotate the hydrogen clockwise to this position, carbon 8 will rotate clockwise to this position. And carbon 5 will rotate clockwise to this position. And carbon 5 will still be attached to carbon 6. Now, in order to achieve this rotation, we must be rotating the molecule around the carbon 3, carbon 4 bond. But that is legal. We know that there is free rotation around a single bond in a straight chain. This is a single bond in a straight chain, so we know there's free rotation around this bond. So we know that there's nothing to prevent us from rotating this hydrogen over to this position. And that's the whole purpose of the Newman projection. The Newman projection is just an easier way to rotate around a single bond. The purpose of a Newman projection is that it gives us an easier way to rotate a molecule around a single bond. You could rotate around the single bond using this picture, but most beginning students find it easier to rotate around the 3,4 single bond using a Newman projection. Remember that we're trying to compare the leaving group and the beta hydrogen. And now we've accomplished what we wanted because now those two groups are anti from each other. In this Newman projection, the leaving group and the beta hydrogen are anti to each other. The leaving group and the beta hydrogen are anti to each other. That means that they are in the anti-periplanar conformation that's required for E2. They're automatically going to be in the same plane now as well. So they are anti-periplanar, and now we can carry out our E2 mechanism. We're ready now to draw the E2 product with the correct stereochemistry. Now, normally we would first draw the E2 mechanism, the electron pushing arrows, and then draw the product. But it's actually not possible to draw the electron pushing arrows completely accurately in a Newman projection. The Newman projection doesn't explicitly show the bond between carbon 4 and carbon 3, between the alpha and beta carbons, and that makes it impossible to draw completely accurate electron pushing arrows in a Newman projection. As a result, I think it's more confusing than it's worth to try to draw the mechanism for a Newman projection. So when we use a Newman projection, we're just going to draw the product directly without drawing the electron pushing arrows. So I won't draw any electron pushing arrows here. Let's just draw the product. We can do that because we have memorized that E2 creates an alkene product. So I can start by drawing the core of the alkene. Remember, the core of the alkene will be a carbon-carbon double bond. And we should be numbering each atom as soon as we can. This will be a carbon-carbon double bond between which two atoms? Between the alpha and beta carbons. The alkene always pi bond, the pi bond in the alkene always forms between the alpha and beta carbons. So we know that this will be carbon 3, the former alpha carbon, and this will be carbon 4, the former beta carbon. E2 forms an alkene double bond between the former alpha and beta carbons. Now, who should be attached to carbon 4? Well, we can see from our Newman projection that carbon 4 is attached to carbon 5 and carbon 8. Carbon 4 should be attached to carbon 5 and carbon 8. 5 and 8. And of course, carbon 5 is attached to carbon 6. Notice how carbons 5 and 8 are both attached to the dot in this picture, which represents carbon 4. All right, now here's carbon 3, and we know carbon 3, the big circle, is attached to carbon 2 and to carbon 7. But where should we draw carbon 2 and carbon 7? This is where we have to get the stereochemistry correct. Should I draw carbon 2 on this side of the double bond, or should I draw carbon 2 on this side of the double bond? Well, here's the point where it's crucial to use this conformation of the Newman projection. So we've completed this step. We rotated our Newman projection so the leaving group and the beta hydrogen are anti. We've rotated our Newman projection so the leaving group and the beta hydrogen are anti. And now we can use this Newman projection in this step. The substituents which are now on the same side of the Newman projection will also be on the same side of the double bond in the alkene product. So this is the key for getting the correct stereochemistry. And now let's illustrate how that's going to work. Well, notice here that in our Newman projection, carbon 5 is on the same side of the Newman projection as carbon 2. That means that carbon 2 should be on the same side of the double bond as carbon 5, and carbon 2 will be attached to carbon 1, like so. So these substituents which were on the same side of the Newman projection end up on the same side of the double bond. They end up cis to each other in the double bond. That's how we use this Newman projection to get the right stereochemistry for our alkene product. And again, we can see that in this Newman projection, carbon 8 is on the same side of the Newman projection as carbon 7. That means that carbon 7 should be on the same side of the double bond as carbon 8. That is, carbon 7 and carbon 8 end up cis to each other in the alkene. So carbon 5 and carbon 2, which were on the same side of this Newman projection, end up cis to each other in the alkene. Carbon 8 and carbon 7, which were also on the same side of the Newman projection as each other, end up cis to each other in the alkene. That's the way in which we can use this Newman projection to determine the correct stereochemistry for our E2 alkene product. So now we've illustrated this three-step method for figuring out the correct stereochemistry for the E2 product. First, we drew the Newman projection based on our original bond line picture. Here was our first Newman projection, but we couldn't use this Newman projection for the product because in this Newman projection, the beta hydrogen and the leaving group are not anti to each other yet. So we had to go on to step 2. We had to rotate this Newman projection so that the leaving group would be anti to the beta hydrogen. That's the correct thing to do because remember that in an E2 mechanism, the beta hydrogen has to be anti-periplanar to the leaving group. Well, here's the Newman projection where the beta hydrogen is anti-periplanar to the leaving group. Now we use this rotation of the Newman projection to draw the correct stereochemistry of the E2 product. Using this step, substituents which are on the same side of the Newman projection end up cis to each other in the alkene product. And notice that this alkene product really does have interesting stereochemistry because there are two different groups attached to carbon 3, an ethyl and a methyl, and there's also two different groups attached to carbon 4, a ethyl and a methyl. So this alkene product does meet this qualification that we've learned for interesting stereochemistry. And you can see that the stereochemistry of this product is important because if you swapped the positions of carbon 2 and carbon 7, you would get a different product. If you moved this ethyl group down to this position and this methyl group up to this position, you would get a different product with different stereochemistry. If we swapped the positions of carbon 2 and 7, this would be a different molecule. You can see they're different because in this molecule, 7 is cis. You can see that in this molecule, the methyl is cis to the other methyl, and the methyl is trans to the ethyl. But in this molecule, the methyls are trans to each other, and the methyl is cis to the ethyl. These are two different pictures with two different stereochemistry. This is the correct picture for this problem because it comes from this Newman projection, and this would be an incorrect picture for this problem. But if you hadn't drawn this Newman projection, it would be hard to know which was the correct and which was the incorrect picture. Be very careful that you get the right atoms connected to 3 and 4. Remember, the atoms connected to carbon 4 are the atoms that are connected to the dot in this Newman projection. And the atoms that are connected to carbon 3 should be the atoms that are connected to the circle in this Newman projection. So we've applied this guideline. The alpha and beta carbons in the starting material were both stereocenters. So to make sure we were going to get the correct stereochemistry for our E2 product, first we drew a Newman projection. So first we drew this Newman projection. Then we rotated the Newman projection so that the leaving group and the beta hydrogen are located anti to each other. So we took this picture and rotated the hydrogen so that it was anti to the bromine. Then we were able to use this picture to draw the correct stereochemistry for the E2 product. Notice where did this bromine go? Why isn't the bromine in this picture? Well, the bromine is the leaving group. We didn't draw the mechanism, but during the mechanism, this leaving group would leave. That's why it's not here in this picture. And what happened to this hydrogen? Well, this is the beta hydrogen that would be taken by the base. So this beta hydrogen is also not in this picture because it would have been taken by the base in the mechanism. Again, it's probably best not to actually try to draw the electron pushing arrows for the mechanism in the Newman projection. That might be more confusing than it's worth. Now remember that this method that I've used for this problem, using the Newman projections, this may or may not be the method that your professor would use for this problem. You don't have to draw a Newman projection here. It's possible to use this original bond line picture and rotate this original bond line picture so that the leaving group and the beta hydrogen are anti. You could rotate this picture so that the leaving group and the beta hydrogen are anti. Some professors might use that method, but I think that's a more difficult method for a beginning student. Most students, many beginning students have difficulty rotating around single bonds in an ordinary bond line picture. It's much easier to rotate around a single bond in a Newman projection. Remember, that's the whole purpose of a Newman projection, or one of the main purposes. One of the main purposes of a Newman projection is to make it easier to rotate the molecule around a single bond. I'll remind you again that I think it's really crucial to number all the carbons when we're using this method. If you don't number all the carbons, it's really easy to make a mistake when you're transferring back and forth between the Newman projection pictures and the bond line notation pictures. Also, remember that includes especially numbering the circle and the dot. And again, it's very useful to keep labeling the alpha and the beta carbons in all of your pictures as well. In this picture, we might refer to these as the former alpha and the former beta carbons. Now, this is the first problem where we've completely illustrated this method for getting the correct stereochemistry for E2. So likely you did not get this problem right when you tried it first on your own, or if you did get it right, you might not have used the correct method. So if you didn't get this problem right with the correct method when you tried it before, I would suggest that now would be a good time to pause the video and just try this problem again from scratch. Go back to these starting materials and just do this E2 reaction again from scratch without looking at this solution to make sure that you actually have correctly internalized this method. And when you can get this problem correct from scratch, then you're ready to go on and try the next problem in this video. Please pause the video and try this problem. I hope you actually tried this on paper. This is a good test of how well you're understanding this material. Let's start by numbering all the carbons. Notice I really did number all the carbons. We can identify our ionic bond between sodium and oxygen and put in the formal charges. The oxygen, negative oxygen, looks like a nucleophile or a base. Neutral bromine will be a leaving group. Carbon 4 will be our alpha carbon. Carbon 4 is a tertiary alpha carbon because it's attached to 3 carbon chains, carbon 3, carbon 6, and carbon 7. With the tertiary alpha carbon, we're in the bottom row. With O-, we're in the right-hand column of our table. The table predicts E2. Write down the name of the mechanism. For E2, we know we're going to use a base, and we know that O- is a strong base. Let's label our beta carbons. Carbon 3 is a beta carbon, carbon 6 is a beta carbon, and carbon 7 is another beta carbon. Now, we only want the major product, so we have to decide which of those beta carbons we're going to use. Here are our E2 guidelines. We've labeled alpha and beta carbons. We see that all the beta carbons are attached to hydrogens. They all have different connectivity. And we want to use the more substituted beta carbon. Well, let's see here. Carbon 6 is a primary beta carbon attached to one carbon chain, carbon 4. Carbon 7 is a secondary beta carbon because it's attached to two carbon chains, carbon 4 and 8. And carbon 3 is a tertiary beta carbon because it's attached to three carbon chains, carbon 5, carbon 2, and carbon 4. So our most substituted beta carbon is carbon 3. So we're going to be using carbon 3 as our beta carbon. It's the most substituted. So I'll erase this beta and this beta since we're not using those beta carbons. I'll keep this label to show that this is the beta carbon that we're using. Of course, you should check whether we're using tert-butyl oxide. We're not using tert-butyl oxide, so the exception does not apply in this case. Now we check whether the alpha and beta carbon are both stereocenters, and they are. Both the alpha and beta carbon here are stereocenters. Carbon 3 is attached to 4 different groups, and carbon 4 is also attached to 4 different groups. So our approach is to draw a Newman projection. Start by drawing the eye. Here's our eye looking down the carbon 4, carbon 3 bond. You could draw the eye on this side, but to be consistent with the previous examples, I'm drawing the eye on this side. Now we start the Newman projection with a dot and a circle. I'll label the dot as carbon 4, and I'll label, because the dot is supposed to be the carbon that's closer to the eye. The circle represents the carbon further from the eye, which is carbon 3. So I'll label the circle as carbon 3. From the eye's perspective, the bromine would be pointing straight up above the 3,4 bond. So I've drawn the bromine pointing straight up from this eye's perspective. Now the other two substituents go in these positions. Carbon 7 is on a wedge, which is in front of the page, and in front of the page is to the left from the eye's perspective. So this would be carbon 7, which is attached to carbon 8. Carbon 6 is on a dash behind the page, which would be to the right from the eye's perspective. So carbon 6 is pointing down and to the right, and 7 is pointing down and to the left. Now we can deal with carbon 3. From the eye's perspective, carbon 2 is pointing straight down below the 3,4 bond. Here's carbon 2 pointing straight down and attached to carbon 1. Here's the other two positions. We can see here carbon 5 is pointing up, and it's on a dash, which puts it behind the page. Behind the page is the region to the right of this person's perspective. So carbon 5 would be pointing up and to the right from this person's perspective. Finally, there's a hidden hydrogen here that we should draw in. Carbon 5 was on a dash, so the hidden hydrogen should be adjacent and on a wedge. The wedge is in front of the page, which is to the left from this person's perspective. So the hydrogen is pointing up and to the left, which is this position. So we've finished our Newman projection. Make sure that you draw the hydrogen, carbon 5 and carbon 2 attached to the circle, which is carbon 3. And you draw the bromine, carbon 6 and carbon 7 attached to carbon 4, which is the dot. So notice that this bond doesn't start on the dot, it starts on the circle. This starts on the circle, this bond starts on the circle, not on the dot. Now our goal is to look at the leaving group. Here's our leaving group, and the beta hydrogen. So it would help here to label that carbon 4 is our alpha carbon, carbon 3 is our beta carbon. So here is the beta hydrogen. Now notice that in this picture, these two groups are gauche from each other. In this picture, the leaving group and the beta hydrogen are gauche from each other, but we want them to be anti to each other. So we're going to need to rotate. We could rotate either carbon 4 or carbon 3, whichever you like. I guess I'll choose to rotate carbon 4. So I'll rotate the bromine 2 positions to over here. I'm going to rotate the bromine 2 positions to over here, so it will be anti to that hydrogen. I'm going to rotate the bromine 2 positions over to here. And when I do that, that's going to rotate carbon 6 2 positions clockwise over to here. Here's a new position for carbon 6. And carbon 7 is getting rotated 2 position clockwise up to here. And carbon 7 is still attached to carbon 8. Now the advantage of that is now the leaving group and the beta hydrogen are anti to each other. We're ready now to draw the E2 product with the correct stereochemistry. Again, since we're using a Newman projection, I'm not going to try to draw electron pushing arrows for a mechanism. I'm just going to go straight to the product. We can do that because we have memorized that an E2 product is an alkene, a carbon-carbon double bond. Number each carbon as soon as you can. The carbon-carbon double bond is going to be formed between carbon 3, which is our beta carbon, and carbon 4, which is our alpha carbon. And here I'm just drawing the bonds. We know these are the bonds on an alkene, but now I have to figure out who goes on these bonds. Well, we know that carbon 4 is connected to carbon 7 and to carbon 6. 4 is connected to 7 and 6, and of course 7 is connected to 8. Remember, carbon 4 will no longer be connected to the bromine in the product because the bromine will be the leaving group in this mechanism. All right, and now we have to draw who's attached to carbon 3. Well, we know one thing that's attached to, we know carbon 3 here is attached to 5 and 2. But how should we draw those? Should I draw carbon 5 over here, or should I draw carbon 5 over here? Which is the correct stereochemistry? Should 5 be cis to carbon 7, or should 5 be cis to carbon 6? Well, we use this version of the Newman projection. We have drawn our original Newman projection here. Then in our step 2, we've rotated that Newman projection so the leaving group and the beta hydrogen are anti to each other. That's this Newman projection. And now we're ready for our step 3. The substituents which are on the same side of the Newman projection will be on the same side of the double bond. In this rotation of the Newman projection, carbon 5 is on the same side of the Newman projection as carbon 7. Therefore, carbon 5 should be cis to carbon 7 in our alkene product. And in this Newman projection, so notice that who else should be attached to carbon 3? The other thing that should be attached to carbon 3 is carbon 2 on the circle. Well, in this Newman projection, carbon 2 is on the same side of the Newman projection as carbon 6. Therefore, carbon 2 should be on the same side of the double bond as carbon 6. Carbon 2 and carbon 6 should be cis to each other. And we can also draw in that carbon 2 should be attached to carbon 1. So we used step 3. Substituents which are now on the same side of our Newman projection will be on the same side of the double bond. Carbon 7 and 5 are on the same side of the Newman projection, so they end up cis to each other in the alkene. Carbon 6 and carbon 2 are on the same side of the Newman projection, so they end up cis to each other in the alkene. Notice that we're not saying that carbon 7 and carbon 5 should be attached to the same carbon. They're cis to each other on separate carbons. Carbon 6 and carbon 2 are not attached to the same carbon. They're cis to each other on separate alkene carbons. So here's our method. We've used this method to determine the correct stereochemistry for this E2 product. We used this method to determine which substituents should be cis to each other in the product and which substituents should be trans to each other in the product. That's the stereochemistry of an alkene product. Remember that carbon 3 will no longer be connected to this hydrogen because this hydrogen will be taken by the base in the E2 mechanism. Remember again that 5 and 2 are connected to 3 because they're connected to the circle in this picture. And 7 and 6 are connected to 4 because they're connected to the dot in this picture. Take your time, and use the numbers to get the exact right connectivity in this picture. So we've used this Newman projection to draw the alkene product with the correct stereochemistry, and notice that this product really does have interesting, important stereochemistry because there's 2 different groups attached to carbon 3 and 2 different groups attached to carbon 4. If you swapped the positions of carbons 5 and 2, you would get a different molecule. You would get the wrong molecule, the wrong product for this problem. Compare this problem and the previous problem. Notice that in this problem, the methyl groups ended up trans to each other. On the other hand, in the previous problem, the methyl groups ended up cis to each other. So these two E2 products had different stereochemistry. And how did we figure out the stereochemistry correctly? Using this Newman projection approach. First, you draw the Newman projection. Then you rotate the Newman projection so the leaving group and the beta hydrogen are anti to each other. That's this picture and this picture. And then you can draw the E2 alkene product where the substituents which are on the same side of the Newman projection will be on the same side of the double bond in the product. So these substituents were on the same side of the Newman projection, so they're on the same side of the product. These substituents are on the same side of the Newman projection, so they're on the same side of the double bond in the product. Notice this circle here doesn't mean that carbon 7 and carbon 5 are attached to the same atom. These are not attached to the same atom. Carbon 7 is attached to carbon 4 and carbon 5 is attached to carbon 3. We're not circling them here because they're attached to the same atom. I'm circling them to show that they are on the same side of the Newman projection and therefore they should be on the same side of the double bond. Carbon 7 is attached to the dot, and carbon 5 is attached to the circle, so you can see that they're attached to different atoms. Notice that it doesn't do any good to draw the Newman projection unless you rotate it so that the hydrogen and the bromine are, the beta hydrogen and the leaving group are anti to each other. Remember that E2 requires an anti-periplanar conformation between the beta hydrogen and the leaving group. E2 requires the leaving group to be anti-periplanar to the hydrogen, and the way to ensure that is to rotate the Newman projection so that the leaving group and the beta hydrogen are anti to each other. Once you've done that, you can see which groups are close to each other, which substituents are close to each other in that conformation of the Newman projection, and that tells you which substituents should be on the same side of the double bond. That gives you the correct stereochemistry for the E2 reaction. Now let's make some comments. First of all, notice that this is a requirement, not a preference. So notice that this doesn't give us the major E2 product. This tells us the only E2 product. The only E2 product or products come from an anti-periplanar conformation. So this is not how you tell the difference between major and minor. This is how you tell the difference between a possible product and an impossible product. This was a rule that told you the difference between a major and a minor product. But this is a rule that tells you the difference between possible and impossible products. It's a requirement for E2. Next comment, notice that this is a requirement for E2. It turns out that it's not a requirement for E1. This only applies to E2 mechanisms, not to E1. Next comment, notice that you don't always need a Newman projection. You only need the Newman projection if both the alpha carbon and the beta carbon are stereocenters. If both the alpha carbon and beta carbon are stereocenters, that's when you need to draw the Newman projection. If either of them is not, if either the alpha or the beta carbon is not a stereocenter, then you don't need to draw a Newman projection. For example, do you remember this problem that we did in an earlier video? Now notice that in this problem, the alpha carbon is a stereocenter. Carbon 2 is a stereocenter, but carbon 3 is not a stereocenter because it's attached to 2 identical groups, two methyl groups. That's why we didn't need a Newman projection for this E2. We did not need a Newman projection for this E2 because the beta carbon was not a stereocenter. Remember, a stereocenter is a carbon attached to 4 different groups. Carbon 2 here is a stereocenter because it's attached to 4 different groups, a chlorine, a methyl, this carbon chain on the right, and a different type of carbon chain on the left. On the other hand, carbon 3, the beta carbon, was not a stereocenter. Carbon 3 was not a stereocenter because it was attached to 2 identical groups, 2 methyl groups. So because the beta carbon was not a stereocenter, we didn't need a Newman projection for this problem. Remember that an alkene has interesting stereochemistry if each of the alkene carbons is attached to 2 different groups. But this, in this product, carbon 3 is attached to 2 identical groups. Since carbon 3 is attached to 2 identical groups, 2 identical methyl groups, this alkene does not meet this qualification, so this alkene product does not have interesting stereochemistry. Well, remember, the whole purpose of drawing the Newman projection is to determine the E2 stereochemistry. So when the E2 product doesn't have interesting stereochemistry, clearly there's no need for the Newman projection. If you swapped the position of the 2 methyl groups, you would still have the same product. So there was no interesting stereochemistry to figure out here, and there was no need for a Newman projection. In fact, we haven't used a Newman projection for any of the problems in the previous videos in this series, because for all the problems we tried in the previous videos, either the alpha or the beta carbon or both was not a stereocenter. Furthermore, remember that we just said that in order for an E2 to occur, the leaving group and the beta hydrogen must be anti-periplanar to each other, which means that the leaving group and the beta hydrogen must be pointing in opposite directions. Now, we clearly did not draw this mechanism with the chlorine and the hydrogen pointing anti to each other. The chlorine and the hydrogen are not pointing anti to each other in the way we drew the mechanism. In fact, we didn't bother drawing the stereochemistry around carbon 3 accurately at all. Remember that to draw accurate stereochemistry around carbon 3, we'd have to use 2 solid lines, a wedge, and a dash for the tetrahedral carbon. We didn't even bother drawing the stereochemistry around carbon 3 accurately, so we certainly couldn't show the anti-conformation between the leaving group and the beta hydrogen. And all of that is okay. All of that is okay because the main purpose of drawing the correct anti-periplanar conformation is to determine the stereochemistry of the E2 product. So when the E2 product has no interesting stereochemistry, there's usually no need to correctly draw the anti-conformation of the leaving group and the beta hydrogen. We could rotate this picture so that it has a correct anti-periplanar conformation, but there's no need to do that because the main purpose of drawing that correct anti-periplanar conformation would be to get the right stereochemistry for the alkene product, and this alkene product doesn't have any interesting stereochemistry. The E2 mechanism requires an anti-periplanar conformation, but we generally only have to bother to draw that anti-periplanar conformation if both the alpha carbon and the beta carbon are both stereocenters. We said that an E2 mechanism requires an anti-periplanar conformation. But why? Why does E2 require an anti-periplanar conformation? I'll just mention that I'm not going to explain that. I'm not going to explain the reason for this requirement. If you're interested, you should be able to find the explanation for that in your textbook. Please pause the video and try this problem. Now let's discuss. We can start by numbering all the carbons. I will number the carbons like this. Do you know what ET means? ET, you should know, stands for an ethyl group. If you wanted to, you could convert the ET group into the bond line notation for an ethyl group, but it's actually probably simpler in this case just to leave it as ET to avoid cluttering our picture. So I won't bother numbering the separate carbons in the ethyl group. We'll just condense that into the ET symbol. Now, in this case, the formal charge was given for us. We were told that this oxygen has a negative formal charge. which means that the oxygen will act as a nucleophile or as a base. Neutral chlorine we expect to be the leaving group, which makes carbon 1 into our alpha carbon. We identify carbon 1 as a secondary alpha carbon because carbon 1 is attached to two carbon chains, carbon 3 and carbon 2. Secondary alpha carbon puts us in the middle row of our table. O- puts us in the right-hand column of the table. So the table predicts an E2 mechanism. Be sure to write that down. Now that we know this is E2, we know we're going to be using the oxygen as a base, not as a nucleophile, and we know that O- is a strong base. We know we should label the alpha and beta carbons for an E2. Well, in this case, we have two beta carbons. Carbon 3 is a beta carbon, and carbon 2 is also a beta carbon. So we've labeled our alpha and beta carbons. Both of those beta carbons are attached to hydrogens. And let's see. We should use the more substituted beta carbon for the major product. The problem asks for the major product. That's the more substituted beta carbon. Well, carbon 3 is primary, attached to one carbon chain, carbon 1. Carbon 2 is tertiary. Carbon 2 is a tertiary beta carbon because it's attached to three carbon chains, carbon 1, carbon 4, and also this ethyl group. So clearly carbon 2 is the more substituted beta carbon, so I'm going to use carbon 2 as the beta carbon. So I'll erase this label now. We're going to be using carbon 2 as our beta carbon. You should check to make sure whether the base was tert-butyl oxide, but this is not tert-butyl oxide, it's ethyl oxide. So the exception does not apply, and we just go with the main rule. Continuing with our guidelines for a straight chain molecule, the alpha and beta carbons here are both stereocenters. Carbon 1 is attached to four different groups: the methyl, the chlorine, this complicated carbon chain, and a hidden hydrogen. And carbon 2 is also attached to four different groups: a methyl, an ethyl, a hidden hydrogen, and this complicated carbon chain. So we have to use this approach to get the correct stereochemistry for E2. We have to draw the Newman projection, looking down the bond between the alpha and the beta carbon. So start by drawing your eye. I'll draw the eye on the right side of the bond. Begin the Newman projection with the dot and the circle. From this eye's perspective, this ethyl group, I should number the dot and the circle. The dot should be the carbon closer to the eye, which is carbon 2, our beta carbon. And the circle should be the carbon further from the eye, which is carbon 1, our alpha carbon. Now, attached to carbon 2, this eye would see the ethyl group pointing straight up. Here's the ethyl group pointing straight up on carbon 2 from the perspective of the eye. Here's the other two bonds for carbon 2 in the Newman projection. We can see carbon 4 would be pointing down. It's on a dash, which puts it behind the page. Behind the page is to this person's right. So carbon 4 would be in this position, pointing down and to the right. That's the region behind the page from this person's perspective. There's also the hidden hydrogen that we should draw in. Here's the hidden hydrogen that I've drawn in on carbon 2. The hydrogen is on a wedge because this other substituent is on a dash. And I went ahead and drew in the hidden hydrogen on carbon 1 as well. This hydrogen is on a dash because this substituent is on a wedge. Draw the wedges and dashes adjacent to each other. The hydrogen is in front of the page, which would be the region of space to the left from this person's perspective. So the hydrogen ends up over here. Now, for carbon 1 is attached to the chlorine, which would be pointing down from this person's perspective. Here's the chlorine pointing down. Here's the other two bonds for carbon 1. Notice that these three bonds are all attached to the circle, not attached to the dot, to show that they're attached to carbon 1, not to carbon 2. Carbon 3 here is on a wedge in front of the page. In front of the page is to the left from the eye's perspective. So carbon 3 ends up pointing up and to the left from the eye's perspective. The hydrogen is on the dash behind the page, which is to the right from the eye's perspective. So the hydrogen ends up pointing behind the page and to the right. All right, as usual, I think it's important to draw this eye and number all the carbons, including the dot and the circle, to make sure you're getting your Newman projection correct. Now remember, we want the Newman projection to be rotated so the leaving group and the beta hydrogen are anti to each other. Well, here's our leaving group, and where's the beta hydrogen? Notice there's two hydrogens shown here. Is this the beta hydrogen, or is this the beta hydrogen? Well, I hope it's clear this is the beta hydrogen. This is not the beta hydrogen, this is connected to the alpha carbon, right? This hydrogen is on the circle connected to the alpha carbon. We want the beta hydrogen. The beta hydrogen is this one attached to the dot, which is our beta carbon. So if there's multiple hydrogens, make sure you're focusing on the correct one. You want the beta hydrogen to be anti to the leaving group. Well, in this picture, these two groups are gauche, not anti. So I'm going to rotate this hydrogen 2 positions clockwise. I guess I could also, 2 positions clockwise, so that the hydrogen will be in this position where it would be anti to the leaving group. I've rotated this hydrogen to this position so that it's anti to the leaving group. Now when you make that rotation, the ethyl group also gets rotated 2 positions clockwise to this position. The ethyl group will end up over here, and carbon 4 will be rotated 2 positions clockwise to over here. Now we're ready to draw the E2 product because our leaving group and beta hydrogen are rotated anti to each other. Since we're using a Newman projection, I won't try to draw the electron pushing arrows. I'll just go straight to the product. I know that an E2 mechanism creates an alkene product with a carbon-carbon double bond. And that carbon-carbon double bond should be between the alpha and beta carbons. Between carbon 1, which is our alpha carbon, and carbon 2, which is our beta carbon. Carbon 2 here we can see should be attached to carbon 4 and the ethyl group. Here's carbon 2 shown bonded to carbon 4 and the ethyl group. Carbon 2 bonded to carbon 4 and the ethyl group. And now we work on carbon 1, and here's where we have to get the stereochemistry accurately. So let's notice that these substituents are on the same side of the Newman projection, and these substituents are on the same side of the Newman projection. So carbon 1 is attached to this hydrogen. And notice that the hydrogen, so where should I put the hydrogen? Should I draw the hydrogen over here? Or should I draw the hydrogen over here? Should the hydrogen be cis to the methyl group, or should the hydrogen be cis to the ethyl group? Well, in this Newman projection, the hydrogen is on the same side of the Newman projection as the ethyl group. Therefore, the hydrogen should be on the same side of the double bond as the ethyl group. So the hydrogen ends up cis to the ethyl group. And then the other thing attached to carbon 1 is carbon 3, the methyl group. In the Newman projection, carbon 3 is on the same side of the Newman projection as carbon 4. So carbon 3 ends up on the same side of the double bond as carbon 4. Carbon 3 and carbon 4 end up cis to each other. Notice that this E2 product really does have interesting stereochemistry. There's 2 different groups attached to carbon 1, a methyl and a hydrogen, and there's 2 different groups attached to carbon 2, a methyl and an ethyl. So we have to get the stereochemistry correct. For example, you have to decide, should these 2 methyl groups be cis or trans to each other? It turned out that the correct outcome is for these 2 methyl groups to be cis to each other. If you hadn't used this method, you might have gotten this wrong picture. You might have accidentally gotten a wrong picture where the methyl groups were trans to each other, whereas in fact the methyl groups should be cis to each other. That's why we needed this Newman projection approach, to avoid the wrong alkene stereochemistry and get the correct alkene stereochemistry. Remember, this was a problem where there were two prominent hydrogens in this Newman projection. So it was important not to confuse these two hydrogens. Don't confuse the beta hydrogen with this, which is not the beta hydrogen. You can tell this is the beta hydrogen because it's attached to the dot. And the dot, in this case, represented the beta carbon. So we wanted to make this hydrogen anti to the chlorine. It would be impossible to make this hydrogen anti to the chlorine because they're both attached to the same carbon. So don't get confused between the different hydrogens. You can see that it can help to focus your attention if you circle the leaving group and circle the beta hydrogen in the Newman projection. Please pause the video and try this problem. Now we'll discuss the problem together. We can start by numbering all the carbons, including this one and including these. We can identify that the O- is likely to be a nucleophile or a base. Neutral iodide will be a leaving group, which makes carbon 4 into our alpha carbon. That gives us a primary alpha carbon. Carbon 4 is attached to one carbon chain, carbon 3. A primary alpha carbon puts us in the top row of the table. O- puts us in the right-hand column of the table. Now, this table then would normally predict SN2 in this cell. Normally, this table would predict SN2, but remember there's an exception for chert butyl oxide, and you should recognize that this is the structure of chert butyl oxide. So here we're going to have an E2 reaction because we are using chert butyl oxide and a primary alpha carbon. We know that you need to watch out for chert butyl oxide because sometimes using chert butyl oxide can affect the result of the reaction. Write down that this is going to be an E2 mechanism based on the table. We want to label the alpha and beta carbons. So in this problem, there's only one beta carbon. Carbon 3 is the only beta carbon, so clearly that's the beta carbon that we're going to use for this reaction. We don't have to worry about whether we're going to use the more or less substituted beta carbon because, again, there is only one beta carbon for this reaction. But let's think about this guideline. Do we need to draw a Newman projection? Well, we need to draw a Newman projection when both the alpha carbon and the beta carbon, when they're both stereocenters. Now notice that this beta carbon is a stereocenter. This beta carbon is a stereocenter. It is attached to 4 different things, but the alpha carbon is not a stereocenter. A stereocenter should be attached to 4 different groups, but 2 of the groups on carbon 4 are identical. Carbon 4 is attached to 2 identical hidden hydrogens. So carbon 4 is not a stereocenter, and therefore we do not need a Newman projection. We don't need a Newman projection. Instead, we can just go right ahead and draw a regular E2 mechanism. We know that we're doing E2, so we're going to use O- as our strong base, and we know that the beta carbon will act as the weak acid. Since I'm not using a Newman projection, I am going to draw the electron pushing arrows for the mechanism. That requires me to draw in the beta hydrogen. Here's that beta hydrogen drawn in on a dash next to this wedge. Remember that the arrows should go from the base to the beta hydrogen. This is the arrow that shows the base taking the beta hydrogen. Then we need an arrow to show the pi bond forming between alpha and beta carbons. Here's that arrow. And then an arrow to show the leaving group leaving the alpha carbon. Here's that arrow. Now we can draw the products. This arrow tells us to form a bond between the oxygen and this hydrogen. Here I show the hydrogen bonded to the oxygen. The oxygen started negative and lost electrons, so it becomes neutral. This arrow tells us to break the bond between carbon 3 and the hydrogen and form a pi bond between carbon 3 and carbon 4. Here's that new pi bond between carbon 3 and carbon 4. Now carbon 3 in the product is now trigonal planar, so we have to change carbon 5 from a wedge to a solid line. This picture would be mistaken if you leave carbon 5 on a wedge. We have to change the wedge to a solid line to show that carbon 3 is now trigonal planar. This arrow tells us to break the bond between carbon 4 and the iodide. Iodide started neutral and gained electrons, so it becomes negative. This is the product that the professor would probably care about for this problem. The main purpose of this video is to show you how to use Newman projections to get the correct stereochemistry for the E2 product. But the purpose of this problem was to remind you that there are many E2 mechanisms where you don't need to draw the Newman projection. Even when the starting material has a stereocenter, you might still not have to draw a Newman projection. We only need the Newman projection if both the alpha carbon and the beta carbon are stereocenters. In this case, the beta carbon was a stereocenter, but the alpha carbon was not a stereocenter. So we didn't meet this qualification, and therefore we actually didn't need a Newman projection for this problem. You could draw a Newman projection, but it wouldn't be, it's not necessary for the problem. By the way, notice that, in fact, this product, this alkene, does not have any interesting stereochemistry because there's two identical groups attached to carbon 4. To have interesting stereochemistry, each of the alkene carbons would have to be attached to two different groups. Carbon 4 is attached to two identical groups, two identical hydrogens, and therefore there was no interesting stereochemistry in this product. Remember, the whole purpose of the Newman projection is to determine the stereochemistry of the product. So when the product has no interesting stereochemistry, clearly we don't need a Newman projection. I hope you can see that if you swapped the position of carbon 2, if you swapped carbon 2 and carbon 5, if you swapped the positions of the ethyl and the methyl group, you would get another version of the same molecule. Here's what you get if you swap the positions of the methyl and the ethyl group. I hope you can see these are two pictures of the same molecule. You could just, if you just flipped this molecule 180 degrees, you could make it look identical to this one. So it doesn't matter which side of the double bond we put the ethyl group on. Either way, we're going to get the same molecule. Either way, the ethyl group will be cis to one of the hydrogens, but also trans to the other hydrogen. This alkene product has no interesting stereochemistry, and so we didn't need the Newman projection approach. Please pause the video and try this problem. Now let's discuss. We can start by numbering all the carbons, including this one. The formal charge on the oxygen is already drawn in for us. We identify the O- as either our nucleophile or our base. Neutral chlorine is a good leaving group, which makes carbon 2 our alpha carbon, and carbon 2 is a primary alpha carbon attached to one carbon chain. Now we're ready to choose a mechanism. With the primary alpha carbon, we're in the top row of the table. O- puts us in the right-hand column of the table. Well, right-hand column and top row, the table predicts an SN2 mechanism. Make sure you write down the name of that mechanism, SN2. Now we need to be careful to check whether we're using tert-butyl oxide, because that would give us an exception. But this species is not tert-butyl oxide. This is not what tert-butyl oxide looks like. By the way, the name of this species is meth oxide. Meth oxide, because of this methyl group, it's definitely not tert-butyl oxide. So the exception does not apply in this case. Instead, we go with the general rule for this cell, which is SN2. This problem is a little bit of a trap to make sure that you weren't on autopilot. The main purpose of this video series is to practice E2 mechanisms, but when you take your exam, you can't assume that all the problems will be E2. The mechanisms will all be mixed up with each other. So don't assume that the mechanisms are E2 in this video series. Use the table each time to figure out the mechanism, just like you'll have to do when you take your exam. So now we can draw our SN2 mechanism. So now we can see that in this case, the O minus, well, remind yourself what happens in an SN2 mechanism. Do you remember how many steps? How many steps are there in an SN2 mechanism, and what happens in those steps? There's one step in an SN2 reaction. An SN2 reaction involves a nucleophile, not a base. So now I'll update and say that this O minus is a nucleophile and not a base. And we can now identify that carbon 2 is going to play the role of electrophile. Carbon 2 has a delta positive charge because it's attached to chlorine, which is more electronegative than the carbon is. A delta positive is the clue that carbon 2 will be our electrophilic atom. The negative formal charge is a clue that the oxygen can be a nucleophile. The delta positive charge is a clue that carbon 2 can be an electrophile, and we've memorized that neutral chlorine is an acceptable leaving group. Now we can draw the mechanism. Remember, there's one step where the nucleophile joins the alpha carbon. So here's the electron pushing arrow for that. Here's the arrow that shows the nucleophile joining the alpha carbon. Remember, a nucleophile is defined as an electron donor. So the nucleophile goes at the beginning of this electron pushing arrow. Simultaneously, we need another arrow that shows the leaving group leaving the alpha carbon. Of course, I went over SN2 reactions in much more detail in the series on SN2 reactions. Now this arrow tells us to form a bond between the oxygen and carbon 2. We form a bond between this oxygen and carbon 2. The oxygen started negative and lost electrons, so the oxygen changes to neutral. And make sure that you still draw the oxygen bonded to carbon 3. The bond between oxygen and carbon 3 is a covalent bond. We would only break a covalent bond if there was an arrow that told us to break that bond. There's no electron pushing arrow telling us to break the bond between the oxygen and carbon 3, so they should still be attached in this picture. Then this arrow tells us to break the bond between carbon 2 and the chlorine, which I already have. The chlorine started neutral and gained electrons, so that chlorine ends up with a negative formal charge. Here's the product the professor would probably care about. This problem didn't actually ask for the mechanism, so you could get full credit if you just draw the product, but as a beginning student, I encourage you to draw the mechanism anyway, because that's your tool for figuring out the product and understanding the reaction. You definitely need to know what the mechanism is, even if you don't draw it. If you thought that this mechanism was E2, you would get a completely different product, wouldn't you, than if you think that the mechanism is SN2. So it definitely is crucial here to see that the mechanism is SN2 rather than E2. Those give us completely different products. Let's compare this problem that we just completed with this previous problem from this video. Do you remember this problem? Do you see how these problems are similar? They're similar because they both have an O minus, and they're similar because they both have a primary alpha carbon. These both have O minus with a primary alpha carbon. If they both have O minus and they both have a primary alpha carbon, why did they give us different mechanisms? Why was the mechanism here SN2, but the mechanism here E2? Well, because remember that the table tells us that the mechanism for this cell is usually SN2, but there's an exception. The mechanism for this cell is E2 when you use tert butyl oxide and a primary alpha carbon. Well, in this case, we did use tert butyl oxide. This is what tert butyl oxide looks like. So you can see it's important to keep your eye out for tert butyl oxide because that can change the outcome of a reaction. So make sure that you have memorized that with a primary alpha carbon and O minus, usually we get SN2, but you have to watch out for tert butyl oxide because in those conditions, tert butyl oxide gives you E2. So make sure you compare and contrast these two examples and make sure that you can tell the difference between them on the test. So one thing we're seeing here is you have to use this table to figure out the correct mechanism, or at least I think using this table is the best way for most students to figure out the correct mechanism. But obviously that won't work unless you have this table memorized. I think most OChem exams are closed notes where you have to rely on your memory. So if that's the case, you need to have this table memorized. Well, no time like the present. If you haven't done so yet, you should now pause the video and take as much time as you need to memorize this table. That means completely memorizing it, including memorizing which species are at the top of each column. You need to know which species neutral oxygen is in this column, which species is in this column, O- and N-, and which are the species at the top of this column in order to be able to use this table. So pause the video and try to memorize this complete table. And then I encourage you to just take a blank piece of paper, and try to write out the table from memory. And then check it. Keep writing out the table from memory and checking it until you can write the table accurately from memory. You need to keep practicing that over and over so that you know that table like the back of your hand while you're taking your exam. Probably is a good idea when you take your exam to write out the table at the beginning of the exam so you can rely on it, but that will only work if you have the table memorized. Remember, here is a handout that contains this important table. You can find a link to this handout in the video description box. And remember that this handout also contains important information that summarizes what happens in SN2, summarizes what happens in SN1, summarizes what happens in E2, and also summarizes what happens in E1, though we haven't discussed that yet. By the time you take your exam, it's important to have all the information on this handout memorized. At this point, you should have all of this information memorized. You should have all of this information memorized about SN2, SN1, and E2, and you should have this information memorized. Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering all the carbons, including this one. I'm not likely to make a mistake, though, with this carbon, so I won't number that one to have a little less clutter. We can notice an ionic bond and put in the formal charges. And so we can identify some roles. This oxygen is likely to be a nucleophile or a base. Positive sodium will be our spectator ion. Now we should recognize, do you recognize this group? This group is what's called a sulfonate. This molecule is called an alkyl sulfonate because it has an alkyl group, a carbon chain, connected to a sulfonate group. Now you need to know that the sulfonate group is a good leaving group. A sulfonate is a good leaving group. In the first video, we mentioned that neutral atoms are usually not acceptable leaving groups, but there's some important exceptions you need to memorize. Obviously, we know that neutral chlorine, bromine, and iodide are good leaving groups, and you also need to have memorized that neutral sulfonates you should memorize are also good leaving groups. So we expect this neutral sulfonate group to be a good leaving group. We have to identify the alpha carbon. We need to memorize that in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. So the alpha carbon here is carbon 3. Carbon 3 is the alpha carbon attached to the oxygen. This carbon is not the alpha carbon. It's part of the sulfonate group. That was why it wasn't really necessary to number this carbon. So the sulfonate group is a leaving group, but we can be specific and say that this oxygen, this neutral oxygen, is the leaving group atom. This particular oxygen is the atom that we can identify as the leaving group atom, the one that's attached to the alpha carbon. I discussed alkyl sulfonates in more detail in the SN2 video series. Now we have to determine the mechanism. Now the problem told us that the mechanism will be elimination, but that doesn't tell us whether the mechanism should be E2 or E1. the E in E2 and E1, both of those E's stand for elimination. So we still need the table to determine what the mechanism will be. Well, we have a secondary alpha carbon. By the way, I better mention what this is. So this is a capital D. Did you know what this capital D stood for? So you should know that capital D stands for deuterium. Capital D stands for deuterium. Deuterium is an isotope, a variant, a type of hydrogen. That means that the reactivity of deuterium, for our purposes, we can say that the reactivity of deuterium is the same as the reactivity of ordinary hydrogen. So you can just treat this deuterium basically as another type of hydrogen. So with that in mind, we can see that carbon 3 is a secondary alpha carbon because it's attached to two carbon chains, carbon 2 and carbon 6. Clearly this is not a carbon chain, and clearly this deuterium is not a carbon chain. So carbon 3 is secondary. Secondary alpha carbon puts us in the middle row of our table, and we're using O-. So the table predicts an E2 mechanism. So the mechanism here will be E2, and that is consistent with our expectation that we were supposed to draw an elimination product, because the E in E2 stands for elimination. We want to label the alpha and beta carbons. Here's the alpha, and it looks like we have two beta carbons. Carbon 2 is a beta carbon, but did you notice that carbon 6 is also a beta carbon? I think some people might disregard carbon 6 because it's on a dash, but that doesn't stop it from being a carbon. So we have two beta carbons. Carbon 2 and carbon 6 are both attached to carbon 3, our alpha carbon. They both have hydrogens. Carbon 6 has 3 hidden hydrogens, and you can see that carbon 2 has 1 hydrogen that's actually already been drawn in for us. Here's the hydrogen drawn in. So they both have hydrogens. They clearly have different connectivity, so they will result in different products. Clearly the things that are connected to carbon 6 are different than the things that are connected to carbon 2. For example, carbon 6 is directly connected to 3 hydrogens, and carbon 2 is not directly connected to 3 hydrogens. So clearly they have different connectivity. They'll result in different products. Now, we have a rule for figuring out the major product, but notice that that rule is not useful to us here because this problem didn't ask us for the major product. This problem didn't ask for the major product. It just said, draw the elimination products. It just said, draw the elimination products. So I'm going to draw both the major and the minor product in this case. So there's no need to figure out which of these is the more substituted and which is the less substituted beta carbon. This rule is not relevant for this problem because we're not going to try to identify the major product. We're just going to draw both the elimination products. I'm going to start by working out the E2 product using carbon 2 as the beta carbon. So I'll erase this beta label here to show that right now I'm going to use carbon 2 as the beta carbon. But I need to remember that eventually I need to go back and use carbon 6 as the beta carbon if I want to show both elimination products. Now we can move to this guideline. We know that sometimes we have to draw a Newman projection. We need the Newman projection if both the alpha and beta carbons are stereocenters. Well, in this case, they both are stereocenters. Carbon 2 is attached to 4 different groups, a methyl, an ethyl, a hydrogen, and this complicated carbon chain. And carbon 3, the alpha carbon, is also attached to 4 different groups, a methyl, the sulfonate, this complicated carbon chain, and the deuterium. Both the alpha and the beta carbon are stereocenters. They're both stereocenters, so we will use a Newman projection to get the correct stereochemistry for the E2 product when we use carbon 2 as the beta carbon. The Newman projection should be drawn looking down the bond between the alpha and the beta carbon. So here's an I that's looking down the bond between carbon 3 and carbon 2, the alpha and the beta carbon. We draw a dot and a circle. The dot represents the carbon closer to the I, carbon 3, our alpha carbon. The circle represents the carbon further from the I, carbon 2, our beta carbon. Remember to number and label those. So from the perspective of this I, the sulfonate group is pointing straight down. Here's our sulfonate group pointing straight down. Here's the other two positions on carbon 3. The deuterium is on the wedge in front of the page. In front of the page is to this person's left. So here is the deuterium. And carbon 6 is on a dash behind the page. Behind the page is to this person's right. From this person's perspective, carbon 1, attached to the beta carbon, is pointing straight up. Here's carbon 1 pointing straight up, attached to this circle, which is carbon 2. Here's the other two positions. This hydrogen is on the wedge in front of the page. In front of the page is to this person's left. So the hydrogen is pointing down and left. Carbon 5 is on the dash behind the page, which is to this person's right. So here's carbon 5. Attached to carbon 4, pointing down and to the right. Make sure carbon 1, the hydrogen, and carbon 5 are attached to the circle, not to the dot. Now our goal is to focus on the leaving group and the beta hydrogen. So remember, our leaving group is the sulfonate. Here's our sulfonate leaving group. And the beta hydrogen is this hydrogen, because this is the hydrogen attached to carbon 2, the beta carbon. A deuterium, remember, is a variation of hydrogen. So a deuterium could theoretically be a beta hydrogen. Deuterium is a variation of hydrogen, so deuterium could theoretically act as a beta hydrogen, but not on this problem, because on this problem the deuterium is attached to the alpha carbon, not to the beta carbon. The deuterium here is attached to the alpha carbon, so we won't use the deuterium as the beta hydrogen. Instead, we'll use the ordinary hydrogen that's attached to carbon 2, our beta carbon. That will be our beta hydrogen. Well, in this picture, these two substituents are gauche to each other, the hydrogen and the sulfonate, beta hydrogen and leaving group. So we need to make a rotation. I'll rotate the beta hydrogen 2 positions clockwise up to here so that it'll be anti to the leaving group. I've rotated the hydrogen up to here so that it'll be anti to the leaving group. That rotation would push carbon 1 clockwise to this position, and carbon 5 would get rotated clockwise to this position. Now we know that the substituents which are on the same side of the Newman projection, substituents which are on the same side of the Newman projection will end up on the same side of the double bond. Substituents on the same side of the Newman projection will end up on the same side of the double bond. Let's draw the alkene product of E2. The double bond is formed between the alpha carbon and the beta carbon, carbon 2 and carbon 3, and I've shown the 4 empty positions here. Well, carbon 3 should be attached to a deuterium and to carbon 6. Carbon 3 should be attached to deuterium and to carbon 6, because those are both attached to the dot. Then carbon 2 should be attached to carbon 5 and carbon 1. Those are attached to the circle. Now notice that in this picture, carbon 5 is on the same side of the Newman projection as the deuterium. So I'll draw carbon 5 on the same side of the double bond as the deuterium, cis to the deuterium. And in this picture, carbon 1 is on the same side of the Newman projection as carbon 6. So I'll draw carbon 1 as on the same side of the double bond as carbon 6. That's this rule. Substituents which are after we rotated the beta hydrogen to be anti to the leaving group, substituents which are on the same side of the Newman projection will also be on the same side of the double bond in the alkene product. That's how this method helps us to get the correct stereochemistry for the E2 product. You can see that this alkene really does have interesting stereochemistry because there are two different groups on carbon 2 and two different groups on carbon 3. Carbon 2 is attached to two different groups, an ethyl and a methyl, and carbon 3 is attached to two different groups, deuterium and a methyl. So it really does make a difference how we arrange these substituents. For example, if you swapped the deuterium and carbon 6, you would get a different product. If you swap the position of the deuterium and carbon 6, you'll get this picture, which is the wrong product. In the correct picture, the two methyl groups are cis to each other. But in this wrong product, the two methyl groups are trans to each other. Those are two different products. We know that this product is correct because it matches with this Newman projection. We know this product is wrong because it doesn't match what was predicted by this Newman projection. Notice that this alkene product is no longer attached to the sulfonate because that would act as a leaving group in the mechanism. And the alkene product is no longer attached to this beta hydrogen because the beta hydrogen would be taken by the base. We didn't show that happening because we didn't draw the electron pushing arrows for the mechanism. Well, we're done with this product, but remember that this problem didn't ask for the major product, it asked for the elimination products. So we should also draw the product that occurs when we use carbon 6 as our beta carbon. So now we need to try this problem again using carbon 6 as the beta carbon. So starting over, I'm going to erase the beta label on carbon 2 and put the beta label on carbon 6 to show that now we're using carbon 6 as our beta carbon. Now, do we need to draw a Newman projection? Well, let's use this rule. We need the Newman projection when both the alpha carbon and the beta carbon are stereocenters. Well, we know that the alpha carbon is a stereocenter, but this beta carbon is not a stereocenter. This beta carbon is attached to 3 identical hydrogens. So the beta carbon here is not attached to 4 different groups. The beta carbon is not a stereocenter, and that means we don't need the Newman projection for this E2 mechanism. We're not going to need to draw the Newman projection here. We would only need the Newman projection if the alpha and beta carbons are both stereocenters. Because this beta carbon is not a stereocenter, we don't need a Newman projection to draw the E2 that involves beta carbon 6. Since I'm not using a Newman projection for this case, I will draw the electron pushing arrows mechanism for this beta carbon. We can start by further identifying the roles. We expect this beta carbon to play the role of weak acid. And we expect this to be our strong base. There's no need to copy the sodium spectator ion here. Up here, I should already have updated that the O- is going to be our strong base in all of these reactions. Now we can draw the electron pushing arrows. We need an arrow for the base to take the beta hydrogen, so I need to draw a hydrogen in on carbon 6. Here's the arrow that shows the base taking the beta hydrogen, then an arrow to show the pi bond forming between alpha and beta carbons. Well, carbon 6 is going to lose this hydrogen, which frees up the electrons in this bond, and we're going to form a pi bond. Remember, we formed the pi bond between alpha and beta carbons, so it helps that we've labeled the alpha and beta carbons here, and I put the head of the arrow on the bond to show the pi bond forming there. And our third arrow showing the leaving group leaving the alpha carbon. Remember, this is the leaving group atom, and it's leaving our alpha carbon. Now we can draw the products. This arrow tells us to form a bond between the oxygen and the hydrogen. I guess I should follow my usual advice and number all the carbons, including this one. Here's the oxygen bonded to the hydrogen. The oxygen started negative and lost electrons, so it ends neutral. This arrow tells us to break the bond between this hydrogen and carbon 6 and form a pi bond between carbon 3 and carbon 6. So here I've drawn that new pi bond between carbon 6 and carbon 3, between the alpha and beta carbons. This Let's see, this arrow tells us to break the bond between carbon 3 and this oxygen. This oxygen starts neutral and gains electrons, so it ends up negative. So here's what the sulfonate leaving group looks like after it has left. Now obviously I haven't finished drawing this alkene product. What else should be attached to carbon 3? Well, we can see here that carbon 3 should be attached to carbon 2 and to the deuterium. So I'll put here carbon 3 is attached to the deuterium and to carbon 2. Notice this product is getting kind of complicated, so I'm using the approach of drawing one atom at a time and numbering each atom before I draw the next one. Carbon 2 we know is going to be attached to carbon 1, carbon 5, and a hydrogen. If you like, you could treat this hydrogen as a hidden hydrogen in the product. Notice that I've tried to orient everything around carbon 2 the same way as in the starting material to make sure that I'm still getting the right stereochemistry here at carbon 2. Is there any reason for the stereochemistry to change at carbon 2? Well, not in this mechanism. Carbon 2 did not participate in this mechanism, so we should not change the stereochemistry at carbon 2 in the product for this mechanism. What should be attached to carbon 6? Well, in this picture, carbon 6 was attached to two other hidden hydrogens. So in this picture, carbon 6 will also, again, be attached to two hydrogens. You can draw those hydrogens in if you like. You can draw these hydrogens in if you like. Or you can continue to treat them as hidden hydrogens and leave them out. So here's our product. Notice that this, in this picture, this 6, the bond between carbons 3 and 6 was a dash. But in this picture, it changed into solid lines, because in this picture, the alkene carbons are trigonal planar. Since these carbons are now trigonal planar, all the bonds are now represented by solid lines, even though this bond was a dash in this picture. And similarly, in this picture, the deuterium was on a wedge, because in this picture, carbon 3 was tetrahedral. But in this picture, carbon 3 is trigonal planar. So in this picture, the bond to the deuterium should change to a solid line. On the other hand, again, notice that we didn't change anything about the bonds around carbon 2. Carbon 2 is still tetrahedral in this picture because it didn't participate in this mechanism. This is a fairly complicated product. When you're drawing a complicated product, when you're drawing a difficult product, it's especially important to make sure that all the carbons are numbered. And I suggest drawing the product one atom at a time. Notice, remember that we started here by drawing the core of the alkene between carbon 6 and carbon 3. And then we added one atom at a time the 4 substituents that were connected here. And we numbered each of them before we wrote down the next carbon. For example, remember, first we drew in the deuterium, then we drew in carbon 2, and we numbered it before going on to say what carbon 2 was attached to. So when you're drawing a difficult product, draw the product one atom at a time and number each carbon before you write down the next carbon. It might help to start with the functional group, start with the alkene, and then gradually show what are the 4 substituents that are attached to the alkene. Most important, take your time and double check yourself. Complicated products are difficult, so take your time when you're drawing them and double check all of your work. Try to be detail-oriented and get all the details right when you're drawing one of these complicated products, because the grader will definitely be detail-oriented and looking for the grader will be looking for little details that you might have gotten wrong, where they can take off credit for your answer. Notice that this alkene product does not have interesting stereochemistry, because this alkene carbon, carbon 6, is attached to 2 identical groups. Carbon 6 is attached to 2 identical hydrogens, so it doesn't match this qualification for having interesting stereochemistry. And you can see the stereochemistry is not interesting here. It doesn't matter in this case whether we put the deuterium on the right or the left. In this picture, the deuterium is cis to one of these hydrogens, and the deuterium is trans to the other hydrogen. And if we had drawn the molecule with the deuterium on the left, we'd have the same stereochemistry. The deuterium would still be cis to one of the hydrogens and trans to the other. So it doesn't matter whether you put the deuterium on the right or the left, you'll get the same product either way. That's what we mean when we say this alkene does not have interesting stereochemistry. That confirms that we didn't need a Newman projection for this problem. Remember, the purpose of the Newman projection is to determine the stereochemistry of the E2 product. This product didn't have any interesting stereochemistry, so there was no need for the Newman projection. We could tell ahead of time. We could tell ahead of time that we didn't need the Newman projection because carbon 6 was not a stereocenter. Now, the products that the professor is probably interested in here are this one and this one. So I'll put these in boxes. These are our two interesting elimination products from this reaction. The interesting thing about this reaction is it gave us a reaction where we had to use both beta carbons. We used both beta carbons because they didn't ask us for the major product, they just asked for the elimination products. So we used both beta carbons. For one of the beta carbons, we had to use the Newman projection approach. Because when we used this beta carbon, both the alpha and the beta carbon were stereocenters. But when we used the carbon 6 beta carbon, we did not need the Newman projection approach because carbon 6 is not a stereocenter. So this illustrates that there are some E2 mechanisms where you need the Newman projection approach, and there's also some E2 mechanisms where you don't need the Newman projection approach. It wouldn't be wrong to use a Newman projection in this case. You could still get a correct answer, but it would be an unnecessary complication to use the Newman projection for this reaction. Also on this problem, we reviewed how to use sulfonate leaving groups. Remember, you can find more details about sulfonate leaving groups in the SN2 series. Also in this problem, we learned how to handle a problem that involves deuterium. Deuterium is a type of hydrogen, and it reacts the same way as hydrogen. In this particular reaction, the deuterium didn't react at all. The deuterium didn't participate in the reaction because it was on the alpha carbon. When you're doing an E2 reaction, you don't use the hydrogen on the alpha carbon. You use the hydrogen on the beta carbon. So since the deuterium was on the alpha carbon in this problem, there was no reason for the deuterium to participate in the reaction. This problem involved a fair amount of work and quite a few steps. And most students, even if they understood the basic idea here, would probably lose a bunch of credit because of careless mistakes or inattention to detail. And the solution to that is, first of all, make an effort to be detail-oriented. Take your time and double-check your work on these problems. And the other solution is practice. The more you practice these types of problems, the fewer careless mistakes you'll make on the exam, and also the better your speed. The more speed you'll be able to build up, you'll be able to build up more speed without making careless mistakes so that you can actually get through all the steps that are necessary on this problem on the exam in a reasonable amount of time. Of course, you should be able to find lots of E2 practice problems in your textbook. At this point, we've covered most of the issues that arise when you're applying E2 to a straight chain. So now would be a good time to go to your textbook and do more E2 problems on straight chains to get extra practice, to help you build up speed and avoid careless mistakes. Comment I forgot to make. Notice how we got the 120-degree bond angles here. 120-degree bond angles. If you had drawn the deuterium in the same approximate position in the answer that it appears in the starting material, this would not have the right bond angles. Obviously, these are not 120-degree bond angles. So notice that we had to really change where the deuterium appeared in the product compared to where it was in the starting material in order to get the correct 120-degree bond angles around the alkene carbon. Time for a brief review quiz. Please pause the video and answer these questions. I hope you actually made an effort to answer these questions. Now let's discuss. These are ideas we talked about in the first video in this series. A base is similar to a nucleophile because both a base and a nucleophile donate electrons. Bases and nucleophiles are both electron donors. So how are they different? Well, a nucleophile donates electrons to join the other molecule, whereas a base donates electrons to take a proton from the other molecule. Those are quite different patterns. Well, we can see that illustrated on these two problems. Remember that this SN2 reaction uses a nucleophile, whereas this E2 reaction uses a base. SN2 here used the O- as a nucleophile, E2 used the O- as a base. Notice that in both cases, the O- was an electron donor. So it goes at the beginning of the arrows. This O- is donating electrons at the beginning of the series of arrows. And this O- is donating electrons at the beginning of the series of arrows. That shows that a base and a nucleophile are similar in that they both donate electrons. But you also can see how they're different. When the O- acts like a nucleophile, it actually joins the alpha carbon. Notice here how the oxygen actually joined carbon 2, the alpha carbon. You can see that here. The nucleophile joins the alpha carbon. So acting as a nucleophile means donating electrons to join the thing that you're attacking. On the other hand, notice that this O- did not join the alpha carbon. This oxygen did not end up attached to carbon 4. Instead, the oxygen just stole a proton from this molecule. This oxygen did not attach to this molecule, it just stole a proton from this molecule. That shows that in this case, the O- is acting as a base, not as a nucleophile. In E2, the base takes the beta hydrogen. It doesn't join the other molecule. So you should carefully compare these two examples so you can understand why we say that SN2 uses a nucleophile, but E2 uses a base. By the way, since a base and a nucleophile both donate electrons, it's not surprising that an atom that can act like a nucleophile might also be able to act in other situations like a base. Notice that a negative charge can be a sign either of a nucleophile or of a base. That makes sense because a negative formal charge makes you want to donate electrons. And if you want to donate electrons, you can be either a nucleophile or a base. A negative formal charge could be a sign either of a nucleophile or of a base. Notice that we can see in our table that O- is both a good nucleophile and a strong base. How do you know which one it will be then? How do you know whether the O- will be a good nucleophile or a strong base? Well, in this context, you use the table to decide how it's going to act. The table told us that in this case, the O- would act like a good nucleophile. And the table told us that in this context, the O- would act like a strong base. So as we discussed in the first video in this series, both a nucleophile and a base donate electrons. A nucleophile donates electrons to join an electrophile, a base donates electrons to take a proton from an acid. Because they're both electron donors, a negative formal charge can be a clue for either a nucleophile or a base. Here's what the electron pushing arrow looks like for a nucleophile. It shows the nucleophile joining the electrophile. Here's what the electron pushing arrow looks like for a base. It shows the base taking a proton from the acid. Well, at this point in the video series, we've discussed most of the issues that are involved with an E2 mechanism on a straight chain molecule. But we still have work left to do because next we have to discuss how to carry out an E2 mechanism on a ring. So next, we're starting in the next video, we'll start talking about how to carry out an E2 mechanism on a ring. The basic ideas that we've discussed so far still apply on a ring, but our method and technique and approach is somewhat different for a ring than for a straight chain. And we'll start discussing that in the next video in this series. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.